Okay, so for our first slide, we're going to be finishing up section 4.1. We had a couple problems left when we left off last Thursday. And so we're here, problem number 34. We're going to analyze the trigonometric function f over the specified interval, stating where f is increasing, decreasing, concave up, and concave down, and stating the x-coordinates of all inflection points. And we're going to confirm our results by looking at the graph on the graphing calculator. Okay, so again, what tells us whether our function is increasing, decreasing is the first derivative. So first thing we have to do is figure out what the first derivative is. So f prime of x is equal to, my function is made by a product, and so then to find the derivative we need the product rule. Take the derivative of the first factor, the derivative of the secant is the secant tangent. Since we already have a factor of tangent, we'll get secant of x tangent squared of x. Plus, we leave the first factor alone and take the derivative of the second one. But the derivative of the tangent is the secant squared, so we end up with the secant cubed of x. To more easily see the sign chart for this function, we can factor out a secant of x. See that they both have a secant of x, and in factored form it's easier to see that. See what the sign chart looks like. And so then that leaves behind the tangent squared of x plus the secant squared of x. Since we have a tangent squared plus a secant squared in the interval from negative pi over 2 to pi over 2, this expression is always positive. In the interval from negative pi over 2 to pi over 2, that's in either, your angle will either be in quadrant 4 or in quadrant 1, so the cosine will be positive. So both factors, the secant of x and the tangent squared of x plus the secant squared of x, are positive, and so our sign chart for the first derivative is pretty simple. It's always positive over the interval from negative pi over 2 to pi over 2. Beyond that, we're not being asked, so we're just being asked in this interval. Concavity is told to us by the second derivative, so we find the second derivative. But before we do that, it might be beneficial to rewrite this first derivative using just the secant function. We can do that by replacing the tangent squared of x with the secant squared of x minus 1, using the Pythagorean identity that the tangent squared of x plus 1 is the secant squared of x. So we can rearrange that to secant squared of x minus 1, and then plus secant cubed of x. And this makes things a little bit easier because now we just have the secant function, and so we have secant cubed of x minus secant of x, and then we have another secant of x over here, so that makes this coefficient a 2. And now our second derivative is a little easier to find. We have the difference of two functions, so the derivative is the difference of the derivatives of each of these two functions. For this function, though, this one is made by a composition, so we just bring down the exponent, 6, take one away from the exponent, and use the same inside. What was inside the power function is the secant, and so we get secant squared of x times the derivative of the inside. And what was inside the secant function is what was inside the cube function is the secant function, and so we get secant of x tangent of x minus the derivative of the secant of x, which is the secant of x tangent of x. And again, notice that they both have a factor of secant of x and tangent of x, so we can factor that out, and we get secant of x tangent of x times 6 secant squared of x minus 1. Again, the secant squared is always going to be a positive number. Multiply it by 6. Not only is it a positive number, it's a positive number bigger than 1, bigger than or equal to 1. So the secant, so if you multiply it times 6, that'll be bigger than or equal to 6, subtracting 1. This is going to be a positive output for this entire factor right here. Same thing for the secant. We're in the interval from negative pi over 2 to pi over 2, so in that interval the secant is positive, and so the only thing that's negative and positive in this interval is the tangent. That one in quadrant 4 it's negative, and in quadrant 1 it's positive. And so then when we go to make our sign chart for our second derivative, we have negative pi over 2 at 0. All of these angles are in quadrant 4, and so there in quadrant 4 your tangent is negative, everything else is positive, so you have a negative output for your second derivative. And once you get past 0, now you're in quadrant 1 and the tangent is also positive, and so then it will all be positive over that interval. So then we are now set to answer the question. This thing is increasing over the interval from negative pi over 2 to pi over 2. The entire time that we are concerned with, this was an increasing function. It was never decreasing. It's concave up over the interval from 0 to pi over 2. And it's concave down over the interval from negative pi over 2 to pi over 2. And that's all we were being asked to do, except to verify this on the graphing calculator. So on the graphing calculator, we go and we put this in. We don't have a secant function on the calculator, so we put 1 over the cosine of x times the tangent of x. We're only interested in this in the interval from negative pi over 2 to pi over 2. So on my window, I put negative pi over 2 to pi over 2, x scale of pi over 12. And I know that the secant and the tangent have asymptotes, so I let the y values go from negative 10 to 10. And when we look at the graph of this, we see that over here at negative pi over 2, we have an asymptote. From negative pi over 2 all the way to pi over 2, this thing is always increasing. From negative pi over 2 to 0, it's concave down. From 0 to pi over 2, it's concave up. And we have an inflection point right here at 0 because it changes concavity. And that's one of the things that we forgot is our inflection point. So the inflection point is at x equals 0. You can see that it changes concavity there. So we're done with that. So let's move on to our next problem. We didn't get a chance to do this one either. So in each part, sketch a continuous curve y equals f of x with the stated properties. So we want to find a curve so that f of 2 is 4, f prime of 2 is 0, and f double prime of x is less than 0 for all x. So I like to organize my work in a sign chart when I can. So we only know the second derivative is always negative. And again, what that tells us is that the graph is concave down. We don't know much about the first derivative other than at 2 we get a value of 0. Okay, so again, let's come over here, and f of 2 is 4 is just telling us that if our input is 2, our output is 4. And we have a point right there. That f prime of 2 is 0 is telling us that we have a horizontal tangent line, that the slope of my tangent line at that point is 0. So you might want to draw the tangent line at that point. You might want to draw it horizontal. And then we're told that our graph is always concave down, right? And so this tells us that our graph is always concave down. So we can come over here to this point. Tangent line's horizontal is telling us our graph is pretty flat there. And there we go. And that would be all.